We're rolling.
We have here today Samantha Jarvis, who's going to construct some dynamic monoidal categories. I'm excited to hear about this. Take it away, Samantha.
Okay, thank you. I hope the mic works and there are no other technical delays. So I am going to do exactly what was just said. I'm going to construct some dynamic monoidal categories. So first, I'm going to give you the entire talk in one slide in a way that is going to be incredibly confusing and make no sense right now. But essentially, the construction that I'm going to walk through in stages is that if we have a category A and a functor to the category of small categories, and then we have a functor to set up, a monoidal natural transformation, we can induce a bunch of structure that's ultimately going to give us a dynamic monoidal category. So that's an incredibly vague way of describing like a lot of constructions. If we have a bunch of functors that satisfy some properties, we get something else out of it. So I'm going to specify what I mean by that a little bit more clearly. So we're going to go through in 5 subsections. We're going to talk about the category org of dynamic organizations and dynamic monoidal categories. Then we're going to talk about what we're calling reverse chain rule categories. We're going to walk through our actual construction, and then we have 2 examples to walk through. So we'll start out where I said we were going to start out. And we're specifically going to start out at a place that's pretty familiar to a lot of people at Topos, at the category of polynomial functors and natural transformations. So we're going to write each of our polynomial functors p as being the sum over I in our position set of y to the set of directions at little I. And then a morphism between polynomials is given by a set map on positions, and then for each position, a way of taking a direction of q to a direction of p. So there's a forward and a backwards component. Okay, so the category poly is monoidal. It has several monoidal structures. It has several monoidal structures it's closed under. The one we're going to be interested in is this tensor, which, given a polynomial p and a polynomial q, the positions of p tensor q are going to be a pair of positions from p and from q, and then the direction set is also given by the product. So for instance, if we had 2 monomials, ay to the a and by to the b, their product is going to be given by aby to the ab. And then this monoidal product is closed. It has an internal Hom, and so this is going to be given by this expression here, which says that for each polynomial morphism from p to q, we're going to raise y to the power sum over directions of p, q to the phi1 of I. So that means we're going to have a pair of a position of p and a direction of q. So for instance, if we were to take the internal Hom of ay to the a and by to the b, we would get b to the a to the ab, y to the ab. Does anyone want me to walk through how exactly we get from this statement to this statement? Because it's not too bad, I would say.
I'd like to see that.
Okay, yeah. So let's do a nice concrete example. So let's think about 2y squared, 3y cubed. So the internal Hom of these polynomials. So if you like the Corolla notation, the tree notation, you have 2y squared and 3y cubed. And so I told you over here that the internal Hom of the 2 of these is going to be, so for each polynomial morphism from p to q, so we should enumerate those. So how many ways can you send 2 things into 3 things? 3 squared. And then for the directions, we have 2 times 3, we have 2 raised to the 3 times 2. And then we'll raise y to the positions of p and then the directions of q. And in this case, all of the Corollas all of the trees in Q, which is 3y cubed, have the same number of directions. So we're going to get 2 times 3. So whatever this coefficient is, y to the power 6. So the internal hom of our two polynomials is again a polynomial, and it's going to respect the expected isomorphism of sets, which is that the polynomial morphisms from p times q to r, the set of those is going to be isomorphic to polynomial morphisms from p to q bracket r. So it's going to respect the tensor hom adjunction. Okay, so another thing we need to talk about the category org of dynamic organizations is the idea of a coalgebra. So in general, given any functor f from set to set, a f coalgebra is going to consist of a set S and then a function phi from S to f of S. So
That's a typo, right? Because the maps to it should be an arrow.
oh yes, that's a typo there. That should be a 2 and not a maps to. So good catch, first typo. We can keep a running track of who finds as many typos. Yes, so it should be phi from f to f of s, not maps to. So in this case, oh, good, okay. David 2, everyone else 0. So in this case, because we have the functor given by the internal hom of p and q, we'll just put that in there. And then a morphism between two PQ coalgebras is going to be a function between the state sets that makes this diagram commute. Concretely, because we can describe what the internal hom of p and q is, we can describe what these PQ coalgebras are. So this is going to be pretty important. So a PQ coalgebra is going to consist of a set of states, then an action map, which is going to send the set of states to the set of polynomial morphisms from p to q. So for each state in here, you get a arrow in poly from p to q. And then again, for each state, a way of updating your state, given a direction and a position of, given a position and a direction of p and q, respectively. Okay, so what is the monoidal double category org? So David has actually talked about org in a couple of previous talks in this seminar. So I'm going to give a little summary. So org is a monoidal double category, so its objects are going to be the same thing as the objects of poly. The horizontal morphisms are the PQ coalgebras. So here, this is a coalgebra. The vertical morphisms are just polynomial morphisms, and then you have, for your squares, morphisms of coalgebras. So I think there's one really good question to get out of this commutative diagram, which is, how do you compose this and this? Because I actually haven't told you what that means, and just looking at this right now, it looks kind of nonsensical. So we're actually going to think about the singleton coalgebra. We're going to imagine this polynomial morphism as being the singleton coalgebra, where for any polynomial morphism from p to q, the singleton coalgebra, which we'll call brackets phi, is going to have a single state set, or a singleton state set, a single state. And then its action map is going to send the single state to phi. And then updates are trivial. So act sends the single state to phi, and update is trivial. So recasting these as singleton coalgebras, we can now make sense of that composition. And we now know what it means for there to be a morphism from this composition of coalgebras to this composition of coalgebras. So it is, in fact, something that makes sense. Okay. So I'm going to tell you how to compose things in org. This is a very wordy slide. Essentially, to compose a PQ coalgebra and a QR coalgebra, to form a PR coalgebra, you're going to take the product of the state sets, your action is going to be given by just composing the action polynomial morphisms that you get. And then update is induced by these two expressions. We're not going to really need to be going into the weeds of how you compose coalgebras. For now, I just want to present the formula. And then on the other hand, I said that this was a monoidal double category, so I should probably tell you what the monoidal product in here is. And in fact, it's given component-wise. So again, you'll take the product of your state sets, and your actions and updates are both defined component-wise. Okay, so we think of org as being a category of dynamic organizations. And I'd like to make it a little bit more precise what I mean by that. Before I do that, questions, comments, concerns? Okay. So a PQ coalgebra as I've said, consists of a set of states, and then for each state, an action map that's a polynomial morphism, and an update that tells us how to get a new state. Tells us new state. So the word dynamic is essentially taking care of the fact that we can update our states, we can change. And then for the organization's perspective, we can recall or observe for the first time that wiring diagrams are like polynomial morphisms. And wiring diagrams tell us how things are organized together. So, okay. Would...
How are wiring diagrams like polynomial morphisms?
That's a good question, Harper. Thank you for asking. So,
Are they like them, or are they actually them?
Wiring diagrams are polynomial morphisms, just to be precise. So let's draw some wiring diagram. Call this P, we'll call this Q, we'll say both of these feed into some R. We'll label our inputs and our outputs very creatively, A, B, C, D, E, F. And then we'll label the whole box by box. So P is a polynomial morphism. P is a polynomial dy to the AB. D tells you your possible outputs. A and B tell you your possible inputs. Q is a polynomial morphism EY to the C. And then R is FY to the DE. So the whole box, the whole wiring diagram, is FY to the ABC. So this wiring diagram is going to be a polynomial morphism, save it back, from P times Q times R to box. So that's to say from DE to F, Y to the A, B, C, D, E to F, Y to the A, B, C. Okay, so on positions, we need a map from DEF to F, and that's just going to be given by projecting onto F. And then on directions, we're going to want DEF times ABC. So it's probably DEF ABC to ABC DE, which again is going to be given by projection. Okay. Yeah.
New to this, the notation, is it when you write products, is it a product of sets, or forget what
Or like DE.
Yeah, DE.
Yeah, this is the product of sets. Yeah. I'm just suppressing the times to make it just a forest of letters as opposed to a forest of letters and times. Yeah. Okay. So that's org, and that's the category that we're going to be enriching over. And in the paper that David wrote with Brandon Shapiro about dynamic operads, dynamic categories, they say that a dynamic monoidal thing is a thing enriched in org, which might be a dynamic thing is a thing enriched in org. Might have added in the word monoidal because I had it on the brain, which is the perspective that we take. So a dynamic monoidal category, or an org-enriched symmetric strict monoidal category, say that 5 times fast, consists of a monoid of objects. To each object, we're going to associate a polynomial, such that we have an isomorphism of polynomials from y, which is the identity in poly under this tensor, to the polynomial we give to the identity in our monoid, an isomorphism of polynomials that respects the monoidal structure. And then to each pair of objects in our original monoid, we associate a specific internal Hom PA prime coalgebra SA A prime. And this association of coalgebras has to respect identitor, compositor, productor, and swapor squares that are subject to coherence equations. So what does that mean? Here is the identitor square. It says that we want a coalgebra morphism from the singleton coalgebra that's given by the identity on A to the coalgebra for SAA. So we have similar ones that basically say we want composition to respect the monoidal product, and then swapper is the symmetry isomorphism in poly. And then the coherence equations we want are standard unitality, associativity behaviors. Okay. All right.
Can you look at the previous slide for a short while?
Yeah.
Okay.
Sorry, I sped through that a little bit.
No, it's
Okay. Great. So let's now talk about reverse chain rule categories, which have a very interesting and kind of suggestive name that we will also talk about. So we're going to start out putting together the first couple of pieces of our 2 commutative triangles that I showed you at the start of the talk. So we're going to assume that we have some monoidal category A, and then we have some functor from A op into the category of small categories. So we can construct the lens category of this functor. Its pairs are going to be, or its objects are going to be pairs of an object of A and then some object of V of A. And then a morphism between 2 such objects is given by an arrow in A and then an arrow from VF of x prime to x in V of A. So if our original functor V was lax monoidal, then lens V will be monoidal itself, where in the first component, the monoidal structure is just given by the monoidal structure on A, and in the second component, we're going to use the lax monoidal structure of our functor. Okay, let's do an example. So we're going to think about the set slice functor from set op to small cats. This is going to send a set cat to the category of set sliced over x, which has as objects set functions with codomain x and as morphisms commutative triangles. So then an arrow or a set function is going to be sent to a functor between set sliced over x prime and set sliced over x by pullback. So if you have some set function with codomain x prime, you pull back along f to get your set function with codomain x. Okay, so if we do this lens construction with set slice, we end up with a category whose objects are given by, well, a pair of some set x and then some set functor with codomain x. And then the morphism here is going to be given by, first we'll just have an arrow from x to x prime and set. And then we'll have an arrow from set sliced over this function f of x prime, so this point to set sliced to the set function whose codomain is x in set sliced over x. So that's this f sharp here. Okay. This is probably boringly familiar to most people here, but the punchline is that this category is actually equivalent to poly. And this is, in fact, the fibrational perspective on poly. So if we have some set function with codomain x, we can get a polynomial whose positions are going to be elements of x, and then the directions at position I will be given by the fiber of this function over I. Okay, so that's going to be another component in our story. Okay, but I still haven't told you what a reverse chain rule category is. So we say that our category A has a reverse chain rule structure with respect to V if the functor from lens V to A that just sends the pair AX to A has a section that is strong monoidal. Okay. Obvious question here, why is this given this name? So, okay. At the start of the summer, maybe I should have started by saying that this has all been joint work with David, and I'm a summer RA at Topos, and the required disclaimer. Okay. I think these. At the start of the summer, our original goal was to show that if you have something called a reverse derivative category, then you can get a dynamic monoidal category with the same objects as our reverse derivative category. So that whole story is going to be our first example from this. So what is a reverse derivative category? So a category is a Cartesian left additive category, or the unfortunate acronym of CLAC. If it is a Cartesian category, that's equipped with a family of monoids for each object. So A, that's subject to axioms that I will not list here. We say that a CLAC is a reverse derivative category if it's equipped with the following additional structure. So we're going to ask that we have a reverse derivative combinator, which says that for any morphism in our category, we get the reverse derivative, which is an arrow from A times B to A.
Can you say who this notion is due to?
This notion is due to, there is a paper. There's definitely, Zanassi and Wilson have definitely done work on this. I don't know if they did the first paper. The first paper is Crockett and a bunch of additional people who might include Zanassi and Wilson. But this notion is due to, yes, at least Crockett and possibly Zanassi and Wilson. Okay. So a reverse derivative category, the reverse derivative combinator is subject to a bunch of additional axioms, which I'm also not going to list here, except for one of them, which is what we call the reverse chain rule. And it's called the reverse chain rule because it's going to look kind of like the chain rule. So it says that if you have f from A to B, and then g from B to C, the reverse derivative of f composed with g is going to be equal to the following string diagram, or expression that we'll express with a string diagram. This probably is completely invisible. Oh, and how much space do I have on the whiteboard? Do I have the whole whiteboard? Okay.
I can move this.
Okay, because if I have the whole whiteboard, I will get out of this like corner. Okay, so the reverse derivative of f composed with g is equal to, well, we have a and c. We're going to split a, and then we're going to run it through f. And then we'll go through R of G, and we'll get out something in B. And then that will go through R of F and give us something in A. So if you kind of squint at this, or if you rewrite this into equational notation, it's going to look a little bit like the familiar chain rule from calculus. Okay. So something that you can show, and I know one direction of this was shown in the RDC paper, and the other direction is not hard, so I think the other direction was also shown, is that if you have lens V down to a Cartesian category A, if you have this functor that's given by AX maps to A, then the functor R is given by the diagonal. So an object A goes to AA. R is a section if and only if A has a differential combinator satisfying the reverse chain rule. Plus one other axiom that we need to make the identities work. Yeah?
Was differential combinating the name you gave?
Yes. So this is the reverse derivative. So the reverse differential combinator. This R brackets.
And also in the theorem, does it have to be a strong monoidal section?
That is an excellent point. Yes, we're going to want that to be strong monoidal. For this statement, no, it doesn't have to be strong monoidal. We're going to always want R to be strong monoidal to make the rest of everything work, but it does not actually have to be strong monoidal to make just this statement work. Okay. All right. Any other questions? Yes.
Wait, on the slide, you have A maps to A, comma RA.
Yes. So.
You mean A, comma A there?
Okay, so that's a really good point, and I'm glad that you said that. So if A is Cartesian, we can ask that R of A is going to be equal to A, but in general, it's not necessarily going to be the case. So we kind of inherit the name reverse chain rule for this slightly more general structure where we're saying, okay, if it has a section that is strong monoidal, then it has a reverse chain rule structure. And in the case where it is actually Cartesian, we can say that is given by the diagonal. Okay, thank you for asking.
Capital R of A is just the name you give to the
Yes.
object
Yes.
in V of A.
Yes. So capital R of A is just the name given to the object in V of A because we have to name it something. Cool. Okay, so let's get to the main construction. So if we think back to when we talked about dynamic monoidal categories, we want some way of taking an object A, an A, and getting a polynomial that's associated with it. So we want a functor from A to poly. So right now, we have a functor R from A to lens V if we assume that A has a reverse chain rule structure. And so now we're going to construct a functor from lens V to poly. And then we'll compose them. We'll be very happy, or we'll be moderately happy. We'll be as happy as these things make you. So I'm going to ask for some extra structure now. I'm now going to ask that I have a strong monoidal functor from A-op to set-op, and that I have a monoidal natural transformation from V to set slice. So this is one of the two triangles that I showed at the start of the talk. A monoidal natural transformation is a natural transformation between lax monoidal functors that respects their monoidal structure, as you would expect from the name. Would anyone like to see the actual definition of that? Are you happy? Okay. So we're adding to our first two pieces of the setup, which were our monoidal category A and our lax monoidal functor V, a strong monoidal functor F, and then a monoidal natural transformation F flat. So this setup is going to induce a functor from lens V to lens set slice, which we know is poly. Okay, so how does it do this? So we want to go from lens V to poly. So on objects, we're going to take a pair AX. So A is an object of A. X is in V of A. And we're going to send it over to F of A. F is a functor from A to set, so that's a set. And then we're going to send it to some set function with codomain F of A. So something that's in set sliced over F of A. So F flat A of X. So this lives in set, and this lives in set sliced over F of A. Now for a second, I'm going to just pull off the notational band-aid a little bit. We're going to want to talk about what the domain of this set function is. So for reasons that are going to be nicer when we're thinking about polynomials, this function goes from F, that's not going to be readable. It's good to test your markers beforehand. Goes from F flat A X of bracket F of A to F of A. So this is F flat A of X. So in examples, this is going to end up being something we can really understand what it is, and for now, this is just slightly clunky notation. So what about on morphisms? So let's recall that a morphism FF sharp in lens V between AX and A prime X prime, for instance, consists of F from A to A prime, and then VF of X prime to X in V of A. So an arrow in V of A. So we're going to send first F to a set function just by hitting it with capital F. So we're going to send it over to F of A to F of A prime under F of F. And then for lens flat of F sharp, lens capital F flat of lowercase f sharp, I promise that once you get into examples, this becomes less soupy, is going to be given by the following expression. So we're going to take the set function, set sliced over F of F, F flat A prime of X prime, to F flat of AX in set sliced over F of A. So we should expect that this is a commutative triangle because it's an arrow and set sliced over F of A. So, okay. Set sliced over F of F flat of A prime X prime is given by a pullback. So what are we going to have? We're going to have F of A prime and then the arrow F flat of A prime, X prime, and then its domain, which I'm going to write as just domain. And then we have F of F from F of A to F of A prime. So if we take the pullback of this arrow here is set sliced over F of F flat of A prime, X prime. So this arrow here is really long thing. You don't really save any time by writing really long thing, but you get a little joke in. Okay, and so now we want a arrow and set sliced over F of A from this to F flat of AX. F flat of AX is an arrow from its domain to f of a. So this is f flat of ax. And so lens f flat of f sharp is that arrow that makes that triangle commute. So we pull back, and then we take an arrow and set sliced over f of a. Okay, any questions about that? Because I think when you see this, it looks kind of hard to know where everything lives, and when you see this, you kind of know where everything lives. Okay. So it's a pretty straightforward computation to show that if our functor f from a to set op is lax or strong monoidal, then that will make lens f flat lax or strong monoidal. So we originally asked that f is going to be strong monoidal. We're going to keep asking that, but we get the monoidality from our functor f. Okay, so now we've returned to the other triangle, and we now have a strong monoidal functor r from a to lens v, a strong monoidal functor lens f flat from lens v to poly, so we can compose them to get the functor from a to poly that we're going to call p. And so this functor is going to send some object a in a to the polynomial whose positions are the elements of the set f of a, and then whose directions are given by the fiber over that position in this set function that we get out of lens f flat. Okay. Would anyone like me to explain that more? I'm seeing nodding, but I'm not sure how to interpret the nodding. Okay.
So what is this p sub a y?
Great question. So,
Find the induced from the r composes lens f flat.
yeah. So, what do I want to say? So, under R, A is sent to A and then this thing R of A, which we remember as just being a name for whatever objective VA we choose to pick. And so then under lens F flat, this gets sent to the pair F of A, and then what we would call F flat of A, R of A. Here R of A is just a new name for X that somehow captures that we've done R in advance. And so we know how to interpret this as a polynomial. So F flat of A, RA is some set function whose codomain is F of A. And so we're going to call the domain of this P of A, F of A. So then at a specific I, we'll just call that P of A brackets I. Yeah.
That's just the name of the codomain.
Yeah.
Whatever element of the slice category.
Yeah.
It's the name of the P bracket I is the name of the fiber.
Fiber over
Yes,
I.
fiber over I.
Fiber over I.
Yeah. You guys are going to be so excited when we get to an example and this all just turns into like FA times FA. Okay, so with all of our setup in place and aware that I'm not entirely sure how much time I have because of when we started, let's define our dynamic monoidal category. So already we can see that this depends on a lot of moving parts. It depends on A, V, F, F flat, and R. So first of all, we're going to essentially always suppress those moving parts. We're going to say that the objects of our dynamic monoidal category are the objects of A, and then the morphisms between A and B are going to be a specific PA-PB coalgebra. Because remember, we want to enrich over org, so we want our arrows in dyne between A and B to be a specific object from org. Okay, so we want that, so our state set is given here. But this kind of feels like something I just conjured out of thin air, so I'd like to walk everyone through where this state set comes from. So while I talk about this, we can just keep this up here and keep in mind this is what we're pushing towards. Okay. So the first fact is that a P coalgebra S phi can be identified with a morphism of polynomials from sy to the s to p. So we're going to let M be some object in A. We can think of this as being a parameter space. And we're going to let move be something in set sliced over f of m that has the same domain and codomain as pm, is what this means. And then we'll let f from mo times a to b be an arrow in our category A. So move is going to tell us how to update. It's going to tell us how to move a parameter. And then f is going to be like an implementation. So we're going to define a PQ coalgebra with state set f of m as follows. So because we have f from mo times a to b, we get some function from pmo times a to pb, and then pm times a is isomorphic to pm times pa. So we have an arrow from pm times pa to pb. And we want something that's going to land. Suppose we want to, this is an error, we want a PA-PB coalgebra. We want something that's going to land in the internal Hom of PA and PB. Can anyone? We're going to do the standard tensor Hom business. We're going to say, okay, this is the same as an arrow from PA, from PM to the internal Hom of PA, PB. Okay, that's good. So the other piece of the puzzle is that we want a morphism of polynomials from fm y to the fm to pm. Okay, so fm and pm have the same position set. So on positions, this is the identity. So ID on positions. On directions, well, we have some direction I, and we can just send it to move I, precisely because move has the same domain and codomain as PM. So if we compose these two maps, we get polynomial morphism fmy to the fm to PA, PB. So we get a PA, PB coalgebra with state set f of m. Okay. The sum of a bunch of coalgebras is also going to be a coalgebra. So we can set our coalgebra to be the sum over m, move, and f as above of f of m, which is exactly the same thing as this set of quadruples over here. For each m move in f, choose an element of fm. Okay. So that's our state set. Any questions about the state set? What about our,
Can we, which part of the, are we constructing the state set is the state set for coalgebra, right?
yes.
Which is representing, is it morphisms in the
Yeah, so the morphisms between PA and PB are going to be given by a coalgebra. And so this coalgebra, I'm saying, is going to have this state set specifically. It's not going to be any coalgebra. We're going to want to pick one.
Right.
And so we're making a specific choice.
So we're in the process of constructing
Yes.
the morphism.
Yes. So I've told you state, and I need to tell you what the actions and updates are.
Are we constructing a specific morphism or the, yeah, we're constructing the set of all morphisms from,
So din AB is going to be this coalgebra.
say that again, what?
So
Yeah, sorry.
din
Oh,
AB
yeah, yeah.
is going to be equal to this coalg
Got it,
that we're
got it.
constructing.
Okay.
Yeah. Yes. Okay. So let's fix a state set, a state in our state set. And so we're going to want to describe the action and the update. So the action is going to be a polynomial morphism from PA to PB. So it's going to have positions and directions. And the update is going to be similarly something that if I give you a position and a direction, you're going to give me back a state set. I think this is a typo. This should be a capital sigma, because we're going to want the update to be I in f of a, PB ff, mi to SAB. Yes. Ooh. Okay. No, we're good. No worries. Delete the last 30 seconds of the recording. Okay, so specifically for the action on positions, we're going to send a position I of f of a to f of mi. This is the only one of these that we can really describe this explicitly in generality. And so for the action on directions and the update, I'm going to show you a commutative diagram that encodes all of these. Again, because we're doing things in generality, this is going to look very unfriendly. But we will walk through it together. So this diagram encodes the information of the action on positions.
Samantha.
Yeah.
So we're 48 minutes in.
Okay.
We can use that information.
I'll use that information as I will. I'm not going to walk us through this. I'm going to go ahead and do one of the examples.
Okay.
So we have here the actions on positions, the action on directions, if you follow this composition, and then the update, because our update map is going to be given by sending a state to the state m, f, move, and then move of our original choice of parameter little m. So eliding the promised explanation, I'll just point out that the existence of the actions on directions and the updates depends on this dotted arrow existing, which is a consequence of the universal property of pullbacks. So, okay, we're going to go through and we're going to do the example in hopefully record comprehensible time. So what are we going to do? We're going to assume that we have some Cartesian category A and some product preserving functor f. You can imagine your Cartesian category is a reverse derivative category if that floats your boat. And for each A in the objects of A, we get a comonad. So we're going to get this comonad A times, which is going to send an object B to A times B, and then it'll send an arrow from B to C in A to A times B to A times C. And we're going to construct the Cochleisly category of this comonad, which the Cochleisly category has the same objects as our original category, and then an arrow from B to C in A to the A times blank is going to be given by an arrow from A times B to C in our original category. Okay. So this gives us a functor, which we call, A to the dot times blank from A op to cat that sends an object to this Cochleisly category. And then sends an arrow to the right arrow by precomposition. I'm going to skip over that. This is a lax monoidal functor. Again, going to skip over that. If we construct the lens category for this functor, we're going to get that we're going to have a pair AX of an object in A and then an object in A, script A to the A times blank, which is just a pair of two objects in A. So here's my little joke. Who's that Pokemon? What's a morphism between two objects in lens of A to the dot times blank?
It's a bimorphic lens.
It's actually Pikachu. But yes, it is a bimorphic lens. So some humor for the 90s kids and Harper. So yes, so as Harper correctly identified, a morphism in here is going to be a bimorphic lens. So say bye-bye to Pikachu because we have to speed through the rest of this. Our natural transformation F flat is going to send a object X of A, or of A to the A times blank, to f of x times f of a to f of a by projecting onto f of a. So then the lens, the lens f flat from lens A to the dot times blank is going to send a pair of objects in A to f(a)y to the f of x. We're going to have R be, as we originally discussed when we were talking about reverse derivative categories, given on objects by the diagonal. So our polynomial, or our polynomial functor is a silly thing to call this because that means something, but P from A to poly is going to send A to f of a, y to the f of a. Okay. So this is our new setup, putting in the information we now have. And our state set is now going to be quadruples of an object in A. Our move function is going to go from f of m times f of m to f of m, f from m times a to b, and then a choice of parameter little m in f of m. And then our actions and updates are going to be of the following form. Okay, and we're going to, plugging back into that original scary looking diagram, we now recover this significantly less scary looking diagram, where we can see that our action on positions, again, is the same, and then our action on directions and our update are now traced around through here. Okay. I'm massively pushing time, so I'm going to suppress that. There is an additional really interesting story to be told here that relates to backprop as a functor that I've kind of been skirting around, and that I think if I had another half an hour I would have gotten through. But yeah, so I will leave it here, and thank you so much.
All right, do we have any questions for Samantha?
Had a question, Mike.
Questions, comments, concerns?
Question. Yeah. Questions for Samantha.
Can you do the canned version of the backprop as functor story? Is there a canned version?
Is there a canned version of that? I don't think I could give a good canned version of that. I think I could give you a kind of stumbling around for 5 minutes of like writing down a bunch of separate facts, but I'm gonna pass on that one to not subject us all to stumbling around.
Could you say a bit more then about what the connection is to backpromise functor, since you mentioned that there is one?
Sure, the non-canned version.
Yeah, or like, without going into like great detail, like what in outline is the connection?
Just the label on the can.
The label on the can. The label on the can is that in backprop as a functor, they talk, or I guess part of the label on the can, the nutritional facts on the can, I don't know, I'm going to get distracted by this metaphor, is that there's this category of learners, and an arrow in the category of learners has a implementation, request, and update that types to look exactly like, or types to look very close to like one of these. So, not sure if that's a very good nutritional label.
Yeah.
Yeah.
So is it?
We could cover that same story with this, right?
Yeah, that I get.
Does it end up
That's
being
so
that
the
base that-
story from backprop as a
Yeah.
functor. The story from backprop as a functor is like one of the examples that you could.
Right,
pull
so you
up.
do get a Oregon-enriched category from that example?
Yes.
Yeah. Okay.
Yeah.
Cool.
That's a much better can label. Thank you, David. Cool. I don't have any more jokes, so I could tell the same joke I told during the.
Should we thank the speaker again?